In this video, we're going to go over some common organic chemistry reactions that you'll need if you're studying for your final exam. So let's begin. Let's say if we have 1-butene, and let's react it with hydrobromic acid. So what's going to be the major product in this reaction? The alkene is a nucleophile, and it's going to react with the electrophile, which is the acid. So it's going to acquire the hydrogen and expel the bromide ion. Now the hydrogen is going to go on the primary carbon of the double bond. And the reason why that happens is so that we can put a positive charge on a secondary carbon. You don't want to put the positive charge on a primary carbon. Secondary carbons, or rather secondary carbocations, are more stable than primary carbocations. And that's why it works this way. If we were to put the hydrogen on the secondary carbon, we would get an unstable primary carbocation. And so that's not going to happen. In the last step, the bromide ion is going to attack the carbocation. It could attack it from the front or from the back, giving us a racemic mixture of products. So we can draw the two products like this. We could put the bromine group in the front, that is on the wedge or on the dash. So on a dash, it's going into the page. On the wedge, it's coming out of the page. So we get a racemic mixture of two products, or two stereoisomers. Now let's say if we have this alkene, what's going to be the major product if we react it with hydrobromic acid? And let's compare that with hydrobromic acid and peroxides. So this is an organic peroxide. Or if you see H2O2, it will have the same effect. Now, HBr without peroxides occurs with Markovnikov regiochemistry. As such, the bromine atom will go on the more substituted carbon atom of the double bond, that is, the tertiary carbon. But when you use an HBr with peroxides, the bromine atom will go on the least substituted carbon atom of the double bond, in this case, the primary carbon. And so you can get those two different products if you use peroxides or not. Now for the next example, we're going to start with cyclohexene. What's going to happen if we react it with bromine using dichloromethane? Dichloromethane is an inert solvent, so it really doesn't do anything. But when you react an alkene with Br2, the reaction proceeds with anti-addition. One bromine atom will be on the wedge, the other will be on the dash. Now you get this product, plus you also get the enantiomer. So you get a mixture of two products. And so those are the products for that reaction. Now let's start with cyclohexene again. What's going to happen if we react this alkene with NBS? What you need to know is that this is a radical reaction, and an allylic hydrogen, that is a hydrogen that's one carbon away from the double bond, will be replaced with a bromine atom. So notice that the double bond is unaffected. It will remain in the same position. Now granted, you could get some resonance structures as well. But for a symmetrical alkene like this, you're only going to get one product. But the end product is going to have the bromine atom that's allylic, or one carbon away from the double bond. Now what if we have an alkane? What if we react it with bromine, but in the presence of ultraviolet light? What's going to happen? This is going to be another radical reaction. It's a free radical substitution reaction. So you're going to replace or substitute a hydrogen with the bromine atom. Now bromine is selective, and so it's going to replace the most substituted hydrogen, that is, the tertiary hydrogen. And the reason for that is because it's going to form a tertiary radical. Tertiary radicals are more stable than secondary or primary radicals. So for radical reactions dealing with bromine will selectively abstract the tertiary hydrogen. If you use chlorine, which is reactive and non-selective, chlorine will give you a mixture of products. It can abstract the primary, secondary, or tertiary hydrogen, leading to a bunch of different products. But bromine is selective, and so the major product will be this one. By the way, if you want a more detailed review on the mechanisms of these reactions, feel free to check the description section of this video, and I'm going to post my playlist, my organic chemistry playlist, where you can find these other videos where I go into the mechanism and explain why these reactions occur the way they do. So I'll have some mechanisms in this video, but a lot of reactions you'll see, I'm just going to summarize the end result. But you can check out my playlist if you want a more detailed review on those reactions. So the next example is going to be the acid catalyzed hydration of an alkene. So let's say if we were to react this with water and hydrochloric acid, which will eventually form the hydronium ion, what's going to happen? What's going to be the major product in this reaction? Now for this one, I'm going to go over the mechanism. When you have an alkene with an acid, the alkene will abstract a proton. The proton is the electrophile, the alkene is the nucleophile. And just like in the reaction with HBr and an alkene, the hydrogen will go on the least substituted carbon of the double bond, in this case the primary carbon. And this is going to put a positive charge on the secondary carbon. Now notice that we have a tertiary carbon next to the alkene. When you see that, a carbocation rearrangement will occur. In this case, a hydride shift. And the reason why this happens is to produce a more stable carbocation. So now that we have a more stable tertiary carbocation, water is going to combine with it. And so we're going to get an oxonium species. Now another water molecule is going to be used as a weak base to remove the hydrogen atom on the oxygen. And so the end result is that we get an alcohol. So whenever you react water with an alkene in the presence of an acid, it will produce an alcohol. And typically the OH group will be found on usually the most substituted carbon. In this case, the tertiary carbon. Now let's go back to cyclohexene. So starting with cyclohexene, what's going to happen if we react it with hydrogen gas using a metal catalyst? The hydrogen atoms will add across the double bond, turning it into an alkane, particularly a cycloalkane. And so we don't have to show the hydrogen atoms in this case, so this is going to be the answer. Now let's use an isotope of hydrogen called deuterium. Now let's use a palladium catalyst instead of a platinum catalyst. Now this time we do need to show the deuterium atoms. And so the double bond will be reduced to a single bond, and we're going to add the two deuterium atoms cis with respect to each other. So this reaction occurs with syn stereochemistry or syn addition. Now you can also draw your product like this. Now it's important to understand that these two compounds are meso compounds. Notice that we have an internal plane of symmetry. They're not enantiomers. So therefore, these are identical compounds, which means we only get one product in this reaction. These two compounds are the same. Now, let's go over the hydroboration-oxidation reaction of alkenes. So we're going to react this with BH3THF with hydrogen peroxide, hydroxide, and water. So what's going to be the major product of this reaction? The first step is called hydroboration, and the second step is oxidation. But combined, the net effect is to convert an alkene to an alcohol without any carbocation rearrangements. So this carbon is secondary and this carbon is tertiary. You need to know that this reaction proceeds with anti-Markovnikov regiochemistry. So what that means is that we're going to put the OH group on the least substituted carbon atom as opposed to the most substituted carbon atom. So the major product will be an alcohol. Now this reaction occurs with syn stereochemistry. And so on the tertiary carbon, a hydrogen will be added, and on the secondary carbon, we're going to put the OH group. So it's going to look like this, which means the methyl group has to be in the back if the hydrogen is in the front. Now, on a typical exam, you may not see the hydrogen, so all you'll see is this product, or it's an enantiomer, or you might see both. So these are the two products that we can get in this reaction. But keep in mind, it's syn addition when you compare the hydrogen and the OH group, because those are the two groups that you're adding across the double bond. But your answer may look like this on a multiple choice final exam. By the way, for those of you who might be studying for the final exam in organic chemistry, I posted a video on my Patreon page, which you can access in the description section of this video. And it's basically a multiple choice practice test with video solutions. So if you need help with the organic chemistry final exam, feel free to take a look at that. But now let's move on. So let's consider this alkene, 1-methylcyclohexene. And we're going to react it with mercury acetate in water, followed by sodium borohydride. So this reaction is called oxymercuration-demercuration. And it's different from the previous reaction. This reaction proceeds with Markovnikov regiochemistry. Now, it's similar to the last reaction in that it will convert an alkene into an alcohol. But the OH group, it's going to go on the more substituted carbon atom of the double bond. So we're going to get a tertiary alcohol in this example. Now, let's go back to cyclohexene. So what's going to happen if we react this alkene with something called MCPBA? MCPBA stands for meta-chloroperoxybenzoic acid. Now, if you see this group, RCO3H, the effect will be the same. What's going to happen is that the alkene will be converted into something called an epoxide. Now, starting with the epoxide, what's going to happen if we react with H2O+? If you see this, it's equivalent to water and HCl. Now, the epoxide is going to open, and we're going to get two diols, anti-addition. So we're going to have two hydroxyl groups. One is going to be on the wedge, and the other will be on the dash. And so we're going to get a mixture of enantiomers, or a racemic mixture of products. So basically, this reaction, these two steps, and this one too, they can convert an alkene into a trans diol. Now, starting with the same alkene, how can we convert it into, let's say, a cis diol? One reaction in which we can do so is osmium tetroxide with sodium bisulfite. And so the end result of this reaction will be a cis diol. So this reaction proceeds with syn stereochemistry. Now keep in mind, this is a meso product, and so there's only one product that we can get. If we draw it the other way, it will be the same as this one. Now let's start with an alkyne, 2-butene. What's going to happen if we react it with hydrogen gas and a platinum catalyst? And let's compare that with sodium metal and liquid ammonia. Now, if you see lithium metal, it will have the same effect as sodium metal because they're both alkali metals. And also hydrogen gas with something called the Lindlar's catalyst. So using the same reactant, what products will we get using these three different reagents? So if we react it with hydrogen gas and the platinum catalyst, the alkyne will be reduced all the way to an alkane. The triple bond will be converted into a single bond. And we need to add 2 equivalents of hydrogen gas to do so. Now, if we react with sodium metal and liquid ammonia, it's going to stop at the trans-alkene level. Now, if we use hydrogen gas and the Lindlar's catalyst, it's going to stop at the cis-alkene level. And so make sure that you understand what each of these reagents will do to an alkyne. So now let's continue. So let's say if we have an alkyne, but instead of an internal alkyne, we have a terminal alkyne. And let's react it with R2BH and THF, followed by hydrogen peroxide and hydroxide. So this is the hydroboration reaction, but for alkynes. Initially, the triple bond will be reduced to a double bond, and we're still going to get Anti-Markovnikov regiochemistry. The OH group will go on the primary carbon as opposed to the secondary carbon. This is called an enol. Now the enol is going to tautomerize into the aldehyde form. And so this is going to be the major product of this reaction. So the hydroboration reaction of a terminal alkyne will give you an aldehyde. Now let's start with the same reagent. The same reactant, propine. But this time, let's react it with mercury sulfate in water and sulfuric acid. So this reaction will proceed with Markovnikov regiochemistry, and so the OH group of the enol will be on the secondary carbon as opposed to the primary carbon. And then this is going to tautomerize into a ketone. And so this is going to be the major product for this reaction. Now let's say if we have acetylene, which looks like this. It's basically a 2-carbon molecule with a triple bond in the middle. What's going to be the major product if we react it with, let's say, sodium amide followed by methyl bromide? So go ahead and try this problem. So what do you think the major product will be in this reaction? So the first thing that's going to happen is the amide ion is going to act as a base. And so it's strong enough to remove the hydrogen of the alkyne. And so this is going to give us the acetylide ion. And then in the second step, it's going to react with methyl bromide. So this is going to be an SN2 reaction. This carbon with the negative charge will attack the methyl group, expelling the leaving group. And so this reaction is a great way to create carbon-carbon bonds. This is going to be the product for the reaction. Now let's work on another example. So starting with acetylene, in the first step we're going to react with NaNH2, and then in the second step we're going to use this time ethyl bromide instead of methyl bromide, and then in the third step we're going to use NaNH2 again, and then in the fourth step we'll use propyl bromide. And then finally in the fifth step we're going to react it with H2 and the Lindlar's catalyst, which you might see it as a mixture of palladium and barium sulfate with quinoline. So go ahead and try this reaction. So we know what's going to happen in the first step. The NH2 minus ion is going to act as a base and deprotonate the acetylene molecule, giving us the acetylide ion. And so this is going to react with ethyl bromide. And so this carbon will attack from the back, kicking out the leaving groups. So we're going to have a total of 4 carbons. So right now what we have is this, if you want to draw the line structure. But I'm going to write this out. So drawing it backwards, it's CH3, CH2 attached to this triple bond. Now we have another hydrogen atom that we can remove. And so let's use this to take off the hydrogen. So now this is going to react with the alkyl halide in step 4, propyl bromide. And so now we should have a total of 7 carbon atoms. Now the last step is to react this with hydrogen gas and the Lindlar's catalyst. So we're going to get an alkene, but the alkene is going to be cis instead of trans. So the 2 hydrogen atoms that will be added across the triple bond will be cis with respect to each other. So the propyl group will be here, and here is the ethyl group. And so this is going to be the final product of this reaction. Now let's say if we have 2-bromobutane. What's going to happen if we react it with potassium iodide and acetone? So here we have a secondary alkyl halide, a polar aprotic solvent, and iodide is a good nucleophile. When you see these conditions favor the SN2 reaction. So the iodide will attack from the back, kicking out the leaving group. Because of that backside attack, we're going to have inversion of configuration, and so the iodide ion will be on the wedge as opposed to the dash. It's on the dash as opposed to the wedge. And so we get the inverted product for an SN2 reaction. So keep in mind, the SN2 reaction works well in polar aprotic solvents. Now let's use the same secondary alkyl halide, but this time we're going to react it with water. Now water is a protic solvent, and even though we have a secondary alkyl halide, protic solvents favor the SN1 and the E1 reaction. So we can get 2 products here, the SN1 product and the E1 product. But for now, let's focus on the SN1 product. So for the SN1 reaction, the leaving group is going to leave. And we're going to get a secondary carbocation. And then water could attack from the front, which will give us the retention product, or it could attack from the back, giving us the inverted product. Now, these 2 products are not equal because we still have the leaving group in its vicinity, and so we're going to get a little bit more of the inverted product, less of the retention, because as water approaches the carbocation, the bromide ion will slightly repel the oxygen part of water as it approaches the carbocation. So we're going to get a mixture of products, but for now, let's continue with the mechanism. So once water adds to the carbocation, we're going to get something that looks like this. And then we need to use another water molecule to take off the hydrogen. So the end result is that we're going to get an alcohol, but an unequal racemic mixture. So these are the SN1 products of this reaction. Now let's try another problem. Actually, let's finish the last problem. We need to do the E1 reaction. So to do the E1 reaction, the leaving group have to leave. And then instead of water coming in and acting as a nucleophile, which will give us the SN1 reaction, first order nucleophilic substitution reaction, water is going to act as a base. And so it's going to go for the adjacent hydrogen, forming an alkene. And so the E1 reaction, the elimination reaction, produces alkenes. We can get the trans isomer, we can get the cis isomer, or water can also go for this hydrogen, giving us the terminal alkene. but this right here is going to be the major product. This is the Zaitsev product. It's the most stable alkene. The Hofmann product, which is this one, that's the least stable alkene. So this right here is going to be the major product, trans-2-butene. But we do get a mixture of all three, so just keep that in mind. Now, what if we were to use, let's say, a strong base? Like, let's use methoxide in water, or rather in methanol. Methoxide is a strong base, and as a result, this is going to favor the E2 reaction, which doesn't produce any carbocation intermediates, and so no rearrangements are possible. The strong base is going to go for the hydrogen, form a double bond, kick out the leaving group all at once. And so the end result is that we're going to get the most stable alkene, the Zaitsev product. Now, if you have a bulky base like terbutoxide, which looks like this, and if the substrate is also bulky, for example, let's say if we have something that looks like that, then the sterically hindered base will prefer to go for the most accessible hydrogen. It's difficult for it to grab this hydrogen because this is a tertiary carbon, and so that hydrogen is sterically hindered by the methyl groups. So it's going to go for the most accessible hydrogen, in this case giving us the Hofmann product. So sterically hindered bases and substrates tend to lead to the Hofmann product, whereas if you have a strong base that is not sterically hindered, or a substrate that is also not sterically hindered, then you're going to get the Zaitsev product. Consider this reaction. Let's say if we have an alcohol and we decide to react it with sulfuric acid and we decide to heat the solution. What's going to happen? This alcohol is a secondary alcohol. And whenever you have secondary and tertiary alcohols, if you react it with an acid and you heat it, dehydration will be favored, and so you're going to get the E1 reaction. And the alcohol will be converted into an alkene. So the first step is protonation by the acid. So you can represent the acid using H+, just to keep things simple. So after protonation, we're going to get a good leaving group. The hydroxyl group is a poor leaving group, but water is a better leaving group. And so water is going to leave. And so we're going to have a secondary carbocation that is adjacent to a quaternary carbon. And so a rearrangement will occur, specifically a methyl shift. And so the whole entire carbon structure will change. This occurs because the driving force is stability. Now we have a more stable tertiary carbocation intermediate. Now, we can use a base at this point. The base could be water, or it could be the bisulfate ion, HSO4-. Now the base is going to go for the hydrogen that will lead us to the most stable alkene. And so it's going to go for this hydrogen, generating this alkene. By the way, before we finish this, notice that the plus charge is here. We could form a double bond here, here, or here. However, the best place to form a double bond is in the middle. So the base is going to go for this hydrogen, forming the double bond in the middle. This is a tetra substituted alkene, and so it's the most stable alkene. Notice that the number of carbon atoms attached to those two double bonded carbon atoms highlighted in red is 4. So this alkene has 4 R groups. It's a tetra substitute alkene. Here are the other alkenes that we can make. We could put a double bond here, or we can put one in this region. So this is a disubstituted alkene because there's 2 carbon atoms attached to any one of these 2 double bonded carbon atoms. A tetrasubstituted alkene with 4 R groups is more stable than a disubstituted alkene with 2 R groups. So therefore, this is the major product. It's the most stable alkene that we can form. Now let's say if we have 2-butanol. What's going to happen if we react it with HBr, and then if we react it with, let's say, PBr3, and finally SOCl2? When you mix HBr or HI with a secondary or tertiary alcohol, it's going to proceed by the SN1 reaction mechanism. If it's a primary alcohol, then it's going to favor the SN2 mechanism. So because this reaction is SN1, we're going to get a racemic mixture of products. So the bromine atom could be on a dash or it could be on a wedge. Now with PBr3, it's going to be an SN2 reaction, and so we're going to get the inverted product. So it's going to be on the dash. It's going to be opposite to what we see here. For the last one, it's going to be an SN2 reaction as well. So we're also going to get the inverted product. Therefore, the chlorine atom will be on the dash. So make sure you know these reactions. They're very common. So let's go over the mechanism for the first reaction, where we had the alcohol, and we're going to react it with hydrobromic acid. So we know it's an SN1 mechanism. The first thing is protonation. We need to turn the poor leaving group into a good leaving group. And so we're going to have OH2, and then water is going to leave now that we have a better leaving group, giving us a secondary carbocation. And then at this point, the bromide ion can either attack from the front or the back, giving us a racemic mixture of products. And so that's how we can convert an alcohol into an alkyl halide. Now let's say if we have 1-butanol, and let's react it with hydroiodic acid. Show the mechanism that will lead to the major product for this reaction. Since we have a primary alcohol, this is going to be an SN2 mechanism. And like the other one, the first step is to convert the OH group into a beta leaving group. Now we're not going to get a carbocation, because if we do, forming a primary carbocation is not good. Primary carbocations are very unstable, so that's not going to happen. This is going to be an SN2 reaction. The iodide ion will come from the back, attack the carbon, and expel the water molecule so that we don't form a primary unstable carbocation intermediate. So this is going to be the end result of this reaction. And so whenever you're dealing with an SN2 reaction, you should not form any carbocation intermediates. Now let's briefly review oxidation reactions. What's going to happen if we mix a primary alcohol with PCC? PCC will oxidize a primary alcohol to an aldehyde. It's a mild oxidizing agent. But let's say if you were to use a strong oxidizing agent, like chromic acid with a primary alcohol, it will oxidize it to a carboxylic acid. Now, if you have a secondary alcohol, it really doesn't matter if you use a mild oxidizing agent or a strong oxidizing agent. The net effect is that it's going to go to a ketone if you use a secondary alcohol. Now, if you're trying to oxidize a tertiary alcohol, let's say with PCC or a chromium reagent, tertiary alcohols are resistant to oxidation, and so you're not going to get any reaction in this example. Now let's talk about reducing agents. Let's say if you have an aldehyde or a ketone and you react it with sodium borohydride. What do you think is going to happen? Sodium borohydride can reduce aldehydes and ketones and even acid chlorides, but it can't reduce esters and carboxylic acids. So in the first example where we have a ketone with NABH4, it's going to reduce it to an alcohol. And the aldehyde will also be reduced to an alcohol. And the way it does this is by adding a hydrogen atom to it, particularly a hydride ion. Now the acid chloride will also be reduced to an alcohol, but by the addition of 2 hydride ions instead. And so sodium borohydride produces alcohols from ketones, aldehydes, and acid chlorides. Now another stronger reducing agent, lithium aluminum hydride, can do all that NaBH4 can, but also it can reduce esters and carboxylic acids. So to predict the product for this reaction, you need to realize that this bond is going to break. And so this group is going to leave. It's going to collect the hydrogen from the solution, turn it into methanol. And the carbonyl group will be reduced to an OH group. And so this will be a product by the addition of two hydride ions. Now, same is true for the carboxylic acid. This is going to grab a hydrogen, so that's going to leave as water. And this is going to be reduced to an alcohol by adding two hydride ions. And so those are two main reducing agents that you need to know. Now, let's talk about the mechanism for this process. So let's use cyclopentanone as an example. And I'm going to reduce it with sodium borohydride. The boron atom has a negative formal charge, and sodium has a positive formal charge. The hydride ion will attack this carbon, causing the carbonyl bond to break. And so we're going to get an alkoxide ion, and here's the hydrogen that we added. And then the alkoxide ion will react with water. It could be H2O plus too, but I'm going to use water. And so that's where it picks up the second hydrogen atom, turning it into an alcohol. But this is the hydride ion that we added to it. And so that's a simple mechanism for the reduction of a ketone into an alcohol using sodium borohydride. Now another reagent you need to be familiar with is the Grignard reagent. So let's react to this ketone with methyl magnesium bromide followed by H3O+. Now the Grignard reagent can reduce a ketone into an alcohol, but by the addition of a methyl group as opposed to a hydride group. So carbon is more electronegative than a metal, so therefore carbon will bear the partial negative charge. So this is a nucleophilic carbon, and it's going to attack the electrophilic carbon of the carbonyl group. This carbon has a partial positive charge, because oxygen is more electronegative than it. And so we're going to add this methyl group to this carbon, and we're going to get an alkoxide ion. And then we are going to acidify the solution. So this is going to pick up a hydrogen, turn it into a tertiary alcohol. And so the Grignard reagent can reduce aldehydes, ketones, and even esters and acid chlorides into alcohols. So this is the final product. So that's it for this video. Thanks for watching.